Hi, and welcome back for your final video tutorial on refining the model. Now that you're familiar with viewing the results from the previous module, we can begin the last part of this course where we will be refining the model by exploring the use of optimization in ANSYS. We will start by going over the different optimization techniques, preparing our model, defining the parameters and how to use the parameter workspace, and then we will use direct optimization to help us refine the model. Finally, we will conclude by going over what we've learned in the course and how it can help you in your future projects. So let's get started. So when we talk about optimization techniques in ANSYS, we can divide them into three main categories. The first would be a manual optimization process, which is you would modify a parameter such as a dimension, and then solve the model and then verify the output such as the stress to check and see if it's better or worse than your previous solution. If not, then you would repeat these steps, change a parameter, solve, verify, etc., which can be very time-consuming. Now, the second one is called parametric optimization, or on the other hand, it's basically an automation of the manual process. So instead of manually going in and checking each parameter and solving it, you can have a program that goes in and changes the model for you. The third type of optimization is called Smart Shape, which uses an adjoint solver which basically runs a topology optimization. To give an example, let's say you have a triangle and you want to optimize the length of one side of the triangle. Well, in this case, it won't change the length of the triangle, but will actually change the shape of the triangle. So this is called the Smart Shape optimization. But for today, we're going to address the second one, which is parametric optimization. So for example, let's say we want to optimize the diameter of the lifting lugs hole. We can tell ANSYS to go through, say, 10 different diameter sizes and generate the safety factor outputs for each one. But of course, as we can see in this example, the smaller the diameter, the larger the safety factor will be. So what we can do is use another parameter, say the mass of the object, and we use that as another constraint in order to find the best diameter while at the same time keeping the mass at a reasonable level. Now, most optimization techniques can be very computationally expensive, meaning that we need a lot of computer power in order to solve these problems quickly. The complexity of our model as it is now is very high, with the use of contacts, multiple bodies, and loading steps. So in order for the following calculations to be completed relatively quickly on your computer, we will need to simplify our model. So let's jump back into Workbench from where we left off in our last tutorial in order to prepare our geometry for the optimization process.